want to make. One is that we, like I said, did start a new unit, and there is a little bit of homework for today. So if you haven't written this down, you can definitely write it down, take a picture, whatever you need. I want to clarify something. Please listen, friends. On page 101, there are actually two different sections with questions on the same page. I don't know who planned that, but that's how it came out. So make sure you look at the formative assessment box. It's question 1, and then those two right there. And then one other note, if you missed the test yesterday, you need to let me know when you're going to do it. If you could take it by Thursday, that would be fantastic, just so that we can get it done and move on, okay? All right, I'm going to click over if that's okay. You guys got your assignments written down if you need them? Here we go. All right, so the warm-up problem says a tennis ball is dropped from a height of 1.6 meters. How long will it take to reach the ground? So we're going to go through this in our nice, thorough way. What's the first thing that you did when you solved this problem? You wrote down your givens. Absolutely, let's write down our little givens list. Who's got a given to tell me? Oh, you guys all had it because I saw you writing. Go, Claire.
The distance is 1.6.
We got 1.6. 1.6 what? Meters. Friends, I'm going to let you know that I've been talking to a lot of people going through problems doing retake prep and that sort of thing, and I see a lot of times when people are writing givens, they'll just write 1.6, and they don't write the meters. Top tip from the physicist right now, you ready? Writing down that unit tells you exactly what kind of number it is. So if you write down that unit, it's going to tell you that it's a what? Acceleration? Velocity? It's going to tell you it's a distance, right? And we know that tennis ball is falling from a height of 1.6 meters. So what is that going to be relative to our problem here? Yeah.
Since it's going down, it will be negative 1.6 meters.
Absolutely it will be. It's going to be negative, and I'm going to write that as delta y. Is everybody okay so far? Issues, questions, or concerns yet? All right, that's one given. I need some more. What else you got? I saw you write, and I saw you had answers even. That means you got them. Then Melissa, go.
Acceleration.
Is what? It is, because we're on Earth, right? We're on Earth, and that tennis ball is going to fall at a rate of negative 9.8 meters per second squared. It's going to speed up as we go. I need something more. What else do you know? Yeah?
Velocity 0.
It for sure is. How do you know that?
Because it was dropped.
It is. So you see, friends, how I've got all of these labeled as something? And you see how they're all with units here? Every time you solve these problems, it's not just a like, oh, it might be a good idea. It's a great idea. Do it. Use that extra graphite. If you need to borrow a pencil because you've been writing too much, then come borrow one from me. I will give that pencil to you so that you can write more units. Okay? I want you to do it. What's the thing? What's your unknown? The next step in the problem? Says how long is time, right? All right. I need an equation. You got your equation sheet out, that nice green piece of paper? There are 4 equations on there. I only want one of them. Which one is the one that I want? I feel like I'm in greasy. Which one is it? Which one? Yeah, okay, good. Thank you. Number 3. Number 3! I don't know what number 3 is. This is my favorite one, though, isn't it? Is it this one? Delta y is equal to VIT plus 1/2 AT squared. If you have not yet made friends with this equation, I'm going to strongly encourage you to do that within the next couple of days. Okay? It's my favorite because we use it a lot in this next unit. Okay? So get to know it. If you're not friends with it, like shake hands, like go out for coffee, whatever you need to do. All right? Anything go to 0 here? Anything go to 0 in this equation?
Yeah.
Yeah. What goes to 0? The VI times the time, right? Because VI is 0. We can solve this for t. You've done this a few times. You're going to do it a few more times this week. Just, fair warning, spoiler alert. What are you doing this week? Solving for t. That's what you're going to do a lot. Okay? Did you get an expression for t? Yes, Miss Carter and I did. What is it? What's your expression for t? He's got it. So I'm going to say like t equals something.
T equals square root 2 delta y over n.
Yeah. Okay. Is this a good equation to memorize?
Yeah.
I mean, being familiar with it is fine. I wouldn't like plug that into your brain to memorize it because it's not always going to be true, but it's a nice thing to be familiar with. Does anybody want me to go from here to here, from the dark green to the light green? Okay, fantastic. We're going to plug in our numbers. Here we go. So we're going to plug them in. So we've got the square root of 2 times negative 1.6 meters divided by negative 9.8 meters per second squared. And you get a time of what? Oh, you guys are so cute because you all have it, I think, don't you? You had an equator, you had a calculator, and you did it. Do it right now. Get out your calculator. Figure out the time right now. Check with your table mate right now. Max, did you and Mercedes check? Do you guys agree on a number? Yeah, what did you get?
0.5.
Did you get that also? Oh, we're not. Oh, I got one for you. There you go. There's always calculators. You can always go to my calculator, friends. What did you get, Mercedes?
0.57 seconds.
0.57 seconds. Don't rely on your table mate. You need to do it too. Because they're not going to sit next to you on your test. They're not going to be able to tell you an answer, so you need to know this. How are we doing? Are we okay? All right, because we're going to move on today. Now, here's a question for you. When we did this problem to figure out how long it was going to take for that object to fall, did it matter what object we were using? Could it have said a frog? How long does it take a frog to fall 1.6 meters? Could it have said a chair? How long does it take a chair to fall 1.6 meters from rest? Could it have been an elephant? How long does it take an elephant to fall 1.6 meters from rest? Sure, as long as we're not worrying about air resistance, it doesn't matter, right? Okay, so does the mass matter at all, friends? We haven't really talked about mass yet, but it's just how much stuff something has, right? Okay, but it doesn't matter. Okay, I just want to make sure that made sense because I need to do a demo for you today. And so I want to make sure that you're not stuck in this little world. So I am going to set up this demo for you, and then I need you to make some predictions. Now, here's something that's really important. It is okay to be wrong. Okay? It is okay to be wrong, and it is okay to learn from being wrong. But the only way that you can learn from being wrong is to do what first? To try, right? You have to try. So I want you to do that. So for our friends at home, for our friends that didn't get to see our fancy demo, we need to write down a couple of things here. You okay? Do you need one more thing? Oh, she's still back there. Sorry. She's trying to be helpful, and yeah, again. All right. So, for our friends at home, I just want to make sure that they know, and that when you get home and you're doing problems like this, that you remember this as well. So this picture up here is very similar. I did not know that Theo was going to be my human ring stand, so I didn't know who to draw, so I just drew a table instead. But it's essentially the same thing. Do you see what I'm saying? So you've got the one that's going straight down, and then you've got the one that's coming out at a funny little arc. Okay? So we're going to take this, and we're going to process what's going on, but the first thing I want to do is to mark a few things. And you might want to do this just in pencil or pen. I'll tell you when the colors are coming. Does that sound good? Okay, so I'll try and do this in black or gray, just so I can kind of keep it consistent with what you got. So the first thing I want to do is to just write down that is object A, the one that is coming straight down here. Friends, I need you to be quiet because otherwise this gets really, really hard to do. We don't have a ton of time, so I want to make sure you're listening. So A is the one that's falling straight down, and then this one over here, this one is object B, I think, from what we were describing before. Is that right? Does that match with what? I just want to stay consistent. Okay? Now, in the demonstration, what was it that we found? Flip it over. Is it, there's nothing on the back? Oh my gosh, did they not, if you didn't get a front and back, you should have one that looks like this. Oh, okay. You should have one that looks like this. Otherwise, yeah, you're like, what is that? That picture does not look the same. We will get there in like a few days, but we're not there yet. Gotta take one step at a time. He was just trying to like overdo it, right? Like, what? just jump in the deep end. We're gonna tiptoe in here. Okay. So, in the demonstration, we had a ball that fell straight down. That was our ball bearing A, and we had B. And what did you find, friends? Tell me what you saw.
They fell at the same time.
They fell at the same time. That is a big deal. You know, because some of you predicted it a different way, that is not necessarily intuitive. And it's really important. That is the thing that makes all of this work. This two-dimensional motion. This motion in the X direction and in the Y direction. The only way that it works is if the time is the same. Okay? So we're going to look at the one that falls straight down because that's the one we know and love the best. Okay? And so you're going to pick one of your colors, and with that color, we're going to talk this through together. But what I would like to draw are some arrows that describe the velocity of ball A as it's falling. So before we draw arrows, because we don't make too big of a commitment yet, tell me about the velocity as it falls. Yeah.
It's increasing.
It's increasing. It's getting more and more. What direction, friends? Negative. So it starts off at 0. How would you draw an arrow to represent 0? Or would you? An arrow to represent 0 is probably going to be pretty much nothing, right? An arrow to represent a little bit is going to be a little longer, and then a little longer, and then a little longer. Are you with me there? Yeah? So we're going to draw that. We're just going to draw arrows. Arrows that represent the motion, the velocity of this ball as it's falling. And so each arrow is going to get longer and longer. Okay? Those arrows, I'm going to write red arrows, or I could use a fancy word. Does anybody know the fancy word starts with a V that represents both, what am I trying to say, magnitude and direction? Vector, right? It's from that movie with that guy. You know what I'm saying, right? Yeah. Red arrows or vectors represent the velocity in the Y direction. Okay? And that velocity in the Y direction gets more negative as time goes on. It gets more negative as time goes on because there is it starts with A. There's something in the Y direction. There's an acceleration. Do you see this little A right over here? Yes, it's there so we can write it down. The acceleration we know is only in the Y direction, in the negative Y direction, and is equal to negative 9.8 meters per second squared. How are we doing? Are we okay? So far, so good? Okay. So that was unit 1. And so we got that. Good for us. But now we're moving over here to what we call two-dimensional motion. So one-dimensional motion is going in one direction. Now that ball, should we do it like this? Was moving both in the X and it was moving in the Y. Okay? How long did this one take to fall as compared to this one? Same time. Here's the weird thing. Are you guys ready for this? Because it's kind of strange. That ball bearing that went over in the horizontal way and started going this way, when it first got a kick, what direction was that velocity in? Which way did it get hit? What's that? That way. In the horizontal direction. Was it given, this is really important, so I want to make sure you hear this. Was it given any velocity in the Y direction to start with? No. It wasn't. It was only given velocity in the X direction. So in the Y direction, it started off with a velocity of 0. And what happened to that velocity in the Y direction as it fell? It increased. It increased because of the acceleration in the Y direction. Are you with me there? So it started off at 0, and then it had a little bit of velocity in the Y direction as it fell, And then that velocity got bigger, and it got bigger, and it got bigger in the y direction. And it's always a little bit hard to do this while I'm standing here talking to you because I want to make sure that I'm as consistent as possible. But this should be about the same length as this one should be the same length as this. All of those red arrows that are matching up should be the same. Okay? In the case for B, this is for A, for B, we can say that the red arrows, or the red vectors, okay, represent the velocity in the y direction. They still just represent the velocity in the y direction. And just like ball bearing A, ball bearing B speeds up in the y direction. Okay? It becomes more negative as time goes on. And it does that because there's acceleration in the y direction. How are we doing so far? Are we okay? You can say no. That's okay. Just need to know where we're at. The motion of ball B was a little different than the motion of ball A, though, wasn't it? Because not only did it fall straight down, it was given a little kick, right? It was given a little kick, and then it just started moving. Yeah? Now, we're going to assume that there's no air, nothing to slow it down, just like the ball and the feathers that fell in that vacuum, okay? That means there's nothing to speed it up or slow it down in the x direction. What would speed it up? Like a little jetpack? Now, Kaylin, you looked at this ball bearing, right? You examined it. Did you see a little jetpack on the ball bearing? I like it when she's like, no, of course not. No, right? There's no jetpack. Okay, one more question, and then you're off the hook. So there's no jetpack. So that would speed it up. Are you with me there? Was there a little tiny parachute? No. Okay. Do you want to look at it again? She still doesn't see a parachute. So there's nothing to speed it up. There's nothing to slow it down. So what does that mean about its velocity in the x direction, you guys? It's the what? I heard somebody say something. The same? It's not going to speed up. It's not going to slow down. That means that there's no acceleration in the x direction. That means that the speed in the x direction is going to be the same the whole darn time. So it's given this initial velocity in the x direction. And that velocity in the x direction is going to be the same the whole time. This one's even harder because I have to draw them all the same. But it's the same the whole time. Okay? Here are the green vectors. What do the green vectors represent? The velocity in the x direction, yeah. And what do you know about the velocity in the x direction as it's going, as it's traveling on its path? It's the same the whole time. It does not change. So we can say that the acceleration in the x direction is equal to 0 meters per second squared. How are we doing? Okay so far? Haley, you look like you're a little confuzzled there. Can I help you with something? You okay?
I'm
Okay.
just like
Trying to keep up? Yeah.
using different colors on like.
I hear you, yes. And I should have said use red and green, but then yeah, some people are red, green sensitive and so whatever. Yeah, good.
So when you're plugging like values into the original equation, like changing light, will the initial velocity be different than 0?
So that's a super good question, and I appreciate the fact that you're asking. So here's the long version of the answer to your question, okay? Because it leads exactly into where I'm going. This is two-dimensional motion, and the thing that's super important is that the motion in the x direction does not affect the motion in the y direction. at all. You remember, because Theo stood up here not for one test, but for two. Do you remember? We did the one that went, and it wasn't very exciting. He was like, oh, whatever. Should have come get the ball bearing. But then we cranked it, right? We went to number 4. Holy, but yeah, that was big. So that had a really, if I was going to draw that one, these arrows would be really big, the green arrows would be, right? Because they had a lot of velocity. But did that affect its motion in the y direction at all? It didn't. So when you do this, when you solve these problems, you're going to solve the x stuff and the y stuff completely separately. That's the key. Okay? We'll do this tomorrow, but you might want to even just write yourself a note right over here. We're just going to write it down right now since we're here. Okay? At the very bottom, there's a thing about setting up the problems. And we'll do that, like I said, later. But let's write this down right now. When we solve, we're going to solve this is a very technical term, X stuff. I'm not going to say horizontal motion, but I like X stuff because it means something to me. Okay, solve the X stuff and the Y stuff completely separately. Separately. Okay? What's the only thing that keeps them together? What's the only thing that they have in common? What's that? They're moving, right? They're absolutely both moving. The thing that I'm thinking about is that both of these are at the same height at the same what? Time. Same time. The time is the thing that ties them together. Yeah. So thanks for asking that question, because that kind of will lead us into what we're doing tomorrow. Tomorrow. Before we do that, though, you may have noticed that there are some graphs there. Do you see those graphs? You've probably gathered that we like graphs, right? I would like for you, you've got a few minutes, to look, let's just do, Natalie, which you want to do, X or Y first? You get to pick. You have control. X. She wants to do X first. I want everybody to look at these horizontal motion graphs. I want you to use the picture you drew and see if you can draw the position, velocity, and acceleration versus time graphs just for the X motion. It's a lot like a buggy traveling along a floor, okay? Or a bowling ball traveling along a floor. See if you can do that. Talk to your table mates. Try it. Use the physics that you know, because you know this. Yeah. Well, ball A doesn't have any, so let's do ball B. Okay. Fair question, but yes. Graph for ball B. Yes, thanks for asking.
So you go one.
And friends, if you get these done, bam, 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 then start the vertical ones, because you can do those too. Okay? The vertical motion, the y direction, is just like the puppy falling, or the ball falling, or the whatever. It doesn't matter. Whatever it is. Give it a try. See if you can do it. You guys can do this stuff. I know you can.